Is it Should I start from? Okay. So we're going to go ahead and get started with this session on novel architectures. So our first speaker is going to be Mohammad Bakhshalipour, who is a PhD candidate in electrical and computer engineering at Carnegie Mellon University. His research lies at the intersection of computer architecture and robotics. And he's going to be presenting his work today on mobile robot path planning. So go ahead.
Thank you. Hi everyone, I'm Mohammad. I'm going to be talking about RACOD, algorithm hardware code design for mobile robot path planning. This work is done in collaboration with my colleagues at CMU and UW. As the title suggests, this project targets robot path planning, mobile robot path planning. Robots are increasingly important in our technological society. The global market capitalization of robots is estimated to reach around $210 billion by 2025, up from $40 billion just in 2017. And this has caused global competition to develop the most sophisticated robots, typically with real-time capabilities and truly autonomous. So the true autonomy requires solving complex AI problems, and to be real-time, robots have to solve those problems at speed, which motivates them to have great compute capabilities. RACOD targets robot path planning, a computationally intensive killer in nearly autonomous robot, and achieves more than 40x performance improvement using hardware acceleration and algorithm extension. So mobile robot path planning, its execution time is dominated by two major components: collision detection, which is done to ensure that the robot would not collide with any of the obstacles in the environment, and path search, which is done for finding an optimal or efficient path from a start point to a goal point. RACOD targets collision detection, improves it using the hardware accelerator, dedicated hardware accelerator, and improves path search process by parallelizing it using an algorithm extension. This is the agenda of the talk. This slide illustrates a very simple path planning scenario into the navigation. A circle-shaped robot tries to reach a goal point from a start point. So the inputs of the problem is a start point, a goal point, and occupancy grid produced by the robot's perception unit, which indicates which points in the environment are free and which are obstacles. Black cells show free points and gray cells show obstacles. And the output of the problem is a path which is typically optimal or efficient and absolutely collision-free. And this all reduces to a graph search problem and is solved using graph search algorithms like Likhachev or ISCA or their variants and extensions. So while path planning is costly, first because collision detection is costly, and second, the path search process is largely serial. Collision detection is costly because we have to check a lot of spaces, a lot of points in the environment to ensure that the robot would not collide with any of the obstacles in the environment. For example, in this example, when we want to check the collision status of a point for this robot, we have to check all those surrounding points for the obstacle to ensure that the robot would not collide with any of them. And execution time can rapidly grow. For example, in the same simple example, when the radius of the robot is 1 resolution unit, we have to check 9 cells at every collision detection operation. But when the radius of the robot is 10 times resolution unit, which is not at all an unreasonable case, we have to check around 400 cells at every collision detection, which is so costly. And the search process to find the optimal path is largely serial. This code snippet shows the core kernel of searching for a process, and at every iteration of the graph search, we expand just one node and then check its successors and then go to the next step. In other words, we don't know which node will be expanded next, so we cannot parallelize the algorithm. And this results in a largely serial execution when we try to find the path between 2 points. RACOD stands for Run-Ahead Collision Detection. It has a collision detection accelerator and an algorithm extension which we name it Run-Ahead State Exploration. The former is a hardware acceleration method and the latter is purely algorithmic. So this is an overview of our hardware accelerator. I'm not going to the details of every component of it, but the most important part of it that results in massively parallelizing the collision detection process is this MapReduce style address generation that resulted instead of performing the collision detection software and checking all those points serially one by one, this MapReduce style address generation generates all the addresses concurrently using different hardware address generation units, and then they are reduced to unit cache blocks, and they finally enter the cache hierarchy. This way we check all of them in parallel. And as a result, we massively parallelize the collision detection process. And the serialization by RACOD attacks this problem by extending the algorithm. The problem is we don't know which node will be expanded next. So the key idea is that instead of actually trying to discover that node, predict it. We try to predict at every iteration, we try to predict the next point or next points and speculatively check their collision status with the current collision detection operations and memorize the result for potential later usage. So whenever we actually expand the predicted nodes, we don't have to wait for collision detection operations because we already have computed the results and memorized them. So with this extension, concurrent with the baseline Borna collision detection operations shown in blue, we can parallelize the predicted nodes collision detection operations. This way, different collision detection operations are parallelized, further improving the performance. So the key here is the prediction mechanism. The prediction mechanism that we use is very simple. The overall scheme of prediction mechanism is learning from past expansions and predicting the next expansion. But we use a very simple predictor, which always predicts that the next step will be the previous direction. Meaning that at every step, they will go the path. It is very likely that we go the path from the direction that led us to the current point. But why does this last direction prediction work very well, we found that because of geometric principles and rules organization. For example, when we want to find the path in a collision-free space from start point to goal point, the shortest path between them is a straight line that connects them. This is a basic geometry principle. And we believe that we show that the organization of real-world environments is not so irregular that could destroy these patterns. Picture a self-driving car navigating in a street, which is bounded by buildings from the surrounding. So even in the case of overtakings and changing lines, the vehicle will mostly move in a straight direction, just like nowadays cars. So we can use this, we can exploit this feature and predict the rest of the path. So to sum up, individual collision detections are accelerated by our hardware accelerator, and different collision detections are parallelized using this algorithmic extension. We synthesize the accelerator using TSMC's 45 nanometer technology. We simulate Intel Core i3, which is a popular embedded processor used in many robots, including our in-house robots. We use this simulator, and the baseline of our implementation is a multi-threaded implementation of A*. These are the results for self-driving car application navigating in a 2D environment. We have chosen the benchmarks from benchmark maps that are snapshots taken from these cities. And as the results show, we have around 40x performance improvement with a run ahead of 32. Run ahead of 32 means that at every step, we predict the next 32 nodes. So we can parallelize their collision detections with the current node. We also evaluate a pilotless drone navigating in a 3D benchmark environment, and we again see the speed ups that reach around 34x with 32 accelerators. These are our prediction accuracy numbers. R stands for run ahead. R, for example, R2 means that at every step we just predict the next node, and 32 means that we predict 31 nodes later. So with increasing the run ahead, it means that the predictor becomes more aggressive, so accuracy drops a little, but the worst case accuracy is still about 85%, substantiating our observation that passes are regular and predictable. You can find more in the paper. We have evaluated stationary robotic arm planning. We have evaluated our technique for stationary robotic arm planning. We have evaluated the total system in GPU. We have evaluated different path planning algorithm and so much else. Finally, the workloads that we have developed for this project are already open source under a broader project named RTR-Bed, which is a benchmark suite for real-time robots. You can access it using this link. And thanks for your attention.
Okay, we have time for questions. Come on up to the microphone.
Very nice work. So I have a question.
Go ahead and introduce yourself.
Yeah, I'm Mulonglo from Cornell University, and I work with Professor Ehsani. So I have a question on the representation of your map. So the obstacles, are they represented by a occupancy grid, or are they represented by some shapes or BVH trees? So how are they represented?
The maps are represented using arrays, like 2D arrays for navigation, 3D arrays for 3D navigation.
So basically like a occupancy grid.
Yes.
Okay, so you are basically parallelizing the collision checking for different.
Yes, the collision detection, the hardware accelerator, which parallelizes the collision detection operation, essentially parallelizes fine-grained cell checking in the occupancy grids.
Yeah, so I'm wondering how does this compare with like collision checking in the ray tracing algorithms?
Well, when the map is represented somehow else, obviously this hardware accelerator is not going to work because the collision detection manner changed. For example, there are revoked collision detection methods like triangle to triangle such things. But this collision detection hardware accelerator works when We have occupancy grid, which is the good thing about the occupancy grid and array is that they can be used in literally every problem. Obstacles can be in literally every shape, but the reworked methods that you are mentioning work in narrow scopes where we can define obstacles to be shaped like circle or very regular types. But this works when with literally any obstacle.
Thanks.
Great, let's have a question from the other side of the room.
Hi, this is Lingy from Rutgers University, and very nice work. Just two quick questions. First one is, I know that in your work, the collision check is just we need to check the occupancy status of the grid is 0 or 1. So I'm a little bit confused why in that status the collision check operation is still costly since we only need to check it. And second question is there any possibility that your accelerator only can be applied on the A* algorithm? Can it be generous to other motion planning algorithms?
Yeah, thank you. Good questions. Why collision detection, which is access to this occupancy grid, costly? Because with growing the robot size, the number of cells that we have to check grows rapidly. For example, in this example, when the radius of the robot, this simple robot is 10 times resolution unit, we have to check around 400 cells at every collision detection operation. So this rapidly grows. When you consider larger robots, this grows to say 1,000 cells. The answer to the latter question is that yes, the hardware accelerator is agnostic to the algorithm. In fact, in the paper, we have evaluated other search mechanisms, past search mechanisms like Dijkstra and weighted A*, as shown here. Yes, they have evaluated Dijkstra, A*, weighted A*, and different heuristics that are used for the search process. You can find the results in the paper.
Okay, thank you.
Sure.
Okay, great question from on this side. Yep, go ahead.
Hello, great work. I'm Yiming from University of Rochester. I got two questions as well. So first, I'm wondering how strong is your motivation as past planning is part of the long pipeline? Is it the bottleneck of the whole process, or how eager it is to speed it up? And my second question is, I saw you had a great improvement on the average latency. How do you look at the variation? Like, do you have any long tail latency problem, and how do you address that?
The first question was about the observation that passes grow regularly. Is that was the question?
Yeah, the first question is path planning, how important it is, basically.
How important the whole path planning process?
In the whole, rollout or your self-driving workloads, how important it is.
In the integrated system.
Right.
Well, it depends on application. I agree that in some applications where we don't have to have a optimal path, the effect of path planning latency is overshadowed by other components like perception unit particularly. But in some applications where we have to find an optimal path, where we have a lot of obstacles in the environment, and we have to find a real-time path, the importance of path planning grows, and its latency dominates the other paths, as simply cited by Intel. Intel's robots essentially offload the path planning process to cloud because they are so costly that cannot be done on the edge processor. And the second question was, sorry, I forgot.
Do you have any tail latency problem? You mentioned
latency?
That, right?
Yeah.
In some cases, it could be very.
This work is just average latency, and we didn't evaluate tail latency.
Okay, thank you.
Okay, another question from the side of the room.
Hi, I'm Mehna Shafi from University of Pittsburgh. Thank you for the great talk. I have one quick question about the address call listing. Is the circuit the same as those in GPUs?
Okay, thanks for the question. If you mean the former GPUs, I mean, particularly before Pascal, no, it is very different because in those GPUs, the coalescing is entirely done by software and it's narrowed to just regular nearby addresses. But in recent GPUs, there's a hardware coalescer which coalesces addresses in hardware it bears some similarities with this, with one key important difference, and that is our circuit supports oriented coalescing, which is not supported in GPUs. So because the robot can have arbitrary orientations, the hardware collision detection accelerator have to support different orientations. This is not supported in GPU, but it is supported in this hardware accelerator.
So you would say it's more sophisticated coalescing.
Yes, in every orientation. It
Orientation.
can, yes.
Okay, thank you.
Okay, we have time for one more question. And while we're doing that, maybe we can have our next presenter go ahead and set up.
Austin Rovinsky, Cornell University. Great work. I have many questions, but I'll try to limit it to just one. So I think you mentioned in the paper that path planning algorithms tend to be very serialized, which because they do pointer chasing when they're expanding the wavefront, which leads to memory bottlenecking. Do you find that when you're doing run ahead with such far depths that the traffic from the run ahead ends up competing with just the base exploration of the path?
You mean the extra traffic that is introduced?
Yeah,
by
the
run-
extra traffic that you introduced by running ahead, does that compete with the path exploration?
I didn't mention that the problem is memory bound. It is computational bound. I mean, you have to wait for the next step. There isn't a significant pressure on memory, at least from the collision detection operations. So those extra operations just introduce power overhead, particularly when the predictions are wrong. Our studies showed that power overhead is negligible, but the memory bandwidth is not a problem for collision detection.
But for the path planning aspect?
Yes, it could be a problem for the path planning in general, particularly when the path grows, when the path is large and we have to evaluate a lot of nodes, but the run ahead method doesn't affect that. This run ahead method just checks collisions ahead of the time, which put virtually zero pressure on memory bandwidth.
I see. Thank you.
Sure.
Okay, let's go ahead and thank Mohammed. Okay, so our next speaker is going to be presented by both Haran Yu and Yang Zhao. Haran Yu is a third-year PhD student, and Yang Zhao is a fourth-year PhD student, both at Rice University. Both are interested in algorithm hardware co-design for efficient machine learning systems, and they'll be presenting EyeCoD today, focusing on the emerging AR/VR technology, which is joint work with collaborators at Rice and Meta. Go ahead.
Thank you. Good afternoon, everyone. I'm Haran Yu from Rice University and the supervision Professor Ian Lin. And today, Yang and I are honored to present our work, EyeCoD, eye tracking system acceleration via FlatCam-based algorithm and accelerator co-design. This work is in collaboration with Dr. Ziyun Li from Meta to ensure our whole system fits the real device scenarios. So the general background is that augmented and virtual reality market is booming. The market will reach over $700 billion by 2025, with a compounded annual growth rate of 73%. Among those AR/VR technologies, eye tracking is an essential human-machine interface in AR/VR devices. There are already a lot of AR/VR devices equipped with such eye tracking modalities, like the PlayStation VR 2. One of the most representative applications is the foveated rendering, for which we render the high-resolution pictures in locations where users are looking at, while leaving the remaining background as low resolution. Despite their promise, there are quite some challenges for eye tracking in AR/VR. That is, to achieve real-time performance, we need at least the 240 FPS, as well as the small form factor for the whole system, and the lower power consumption and higher visual privacy. However, existing works fails to meet such requirements. They only achieve an order of magnitude slower, in other words, 30 FPS, and suffer from large form factor and low visual privacy. So why existing eye tracking system cannot satisfy the requirements? The reason is that they rely on lens-based cameras, which result in limitations such as large form factor, high communication cost between camera and backend processor, as well as low visual privacy. So the natural question is that, can we build a lensless eye tracking system? The answer is yes. We adopted a lensless camera, FlatCam. As shown in the below figure, as compared to lens-based cameras, which require 10 to 20 millimeters between the lens and the sensors, the flat cam only require less than 2 millimeters between the mask and the sensors by replacing the lens with the mask. And also, the sensor measurement is not visible by human eyes, so it also protects the visual privacy. In addition, the reduced form factor also allows us to directly attach the eye tracking processor to the flat cam sensor, in which way it allows us to build algorithm and hardware co-design framework to achieve more than 240 FPS, as well as low power consumptions. So based on above analysis opportunities, we propose FlatCam-based algorithm and accelerator co-design called EyeCoD that incorporating 3 features: sensing processing interface, predict then focus algorithm pipeline, and also the dedicated accelerator attached to FlatCam. Correspondingly, there are 2 challenges to achieve such ecosystem. On the algorithm level, we need to think how to track the FlatCam captured eye images efficiently without compromising the task accuracy. And on the hardware level, we need to think how to leverage and support such EyeCoD algorithm for further boosting the acceleration efficiency. So to tackle such challenges in this work, we propose the first lensless FlatCam-based eye tracking system that features algorithm and accelerator co-design called EyeCoD and makes 3 contributions. On the system level, EyeCoD advocates lensless flat cams instead of lens-based cameras to facilitate the small form factor. And on the algorithm level, EyeCoD integrates a predict then focus pipeline to first predict the region of interest and then predict the gaze estimation based on it. On the hardware level, EyeCoD further develop a dedicated accelerator that can be directly attached to FlatCam sensors to accelerate the EyeCoD algorithm. So here, this slide is the overview of the proposed ecosystem. The core idea is to replace, on the system level, is to replace the lens-based camera with the lensless flat cam. As shown in the visualization, the lensless flat cam help largely shrink the small form factor and only require less than 2 millimeter distance between the mask and the sensor. Note that here, the mask refers to a binary coded mask that are fabricated to encode the input eye images and project it on the sensor. The sensor measurement is shown in the middle. It is not visible by human eyes, so it protects visual privacy. And such sensor measurement will be reconstructed to the original eye images by solving the least square objective function as shown in the blue box, where X is the image to be reconstructed, and Y is the sensor measurement, and phi is the hyperparameters in the mask. The reconstructed image will be further packed into the EyeCoD algorithm, and where the core idea is to first predict the region of interest before estimating the gaze estimations. In the algorithm, we incorporate 2 machine learning models. First is the eye segmentation model to predict the region of interest, and second is the gaze estimation models to predict the gaze directions, which is the 3D vector. To accelerate such 2 machine learning model workloads, the core idea in the accelerator level is to develop a dedicated accelerator attached to FlatCam to accelerate both the computation and data movements. So next, I will zoom in to both algorithm and accelerator parts. For algorithm, the challenge is how to aggressively reduce the model complexity. Our design insight is to perform gaze estimation after extracting the ROIs. That is possible because of one fact, that is, the movement of eyes is much slower than the movement of gaze. That allows us to perform ROI prediction only once per 50 frames, while perform the gaze estimation on each frame. So based on such analysis, we propose the predict then focus pipeline, which incorporates 3 stages. The first stage is to perform image reconstruction after FlatCam, which will incorporate the sensor processing interface to replace both camera sensor and first layer of the eye tracking model by the FlatCam coded mask. And second step is to predict the region of interest. We predict and crop the most informative area like pupil, iris, and scala once only per 50 frames. And the third stage is to estimate the gaze directions based on the extracted ROIs and perform for each frame. So next, Yang will introduce the EyeCoD accelerator.
Thanks. Although the EyeCoD algorithm provides potentials of an efficient eye tracking pipeline, a dedicated accelerator is still needed to fully exploit the potentials of the algorithm. In the following, I will introduce the EyeCoD accelerator's features after analyzing the design challenges and considerations. First, because this algorithm includes two NN models with different number of flops or workloads, different processing frequencies, and a stringent execution order, how to orchestrate these two models is challenging. The bottom figure here shows the pros and cons of two classical workload orchestration modes. As we can see, for the time multiplexing mode, although it can provide a higher use opportunity, it has a large resource requirement, and the peak resource usage is constrained by the ROI prediction model. For the concurrent mode, we can amortize the ROI prediction workload among 50 frames. However, the ROI prediction model has limited reuse opportunity due to the limited number of max assigned to it. So the challenge is, can we marry the best of these two modes in our design? Secondly, for the depth-wise convolutional layers in the model, it has a very low utilization. In our evaluation, the depth-wise convolutional layer only accounts for 7.9% flops in the workload, but consumed 34% of the overall processing time. The reason is that the depth-wise layer has a very limited input activation reuses, and that's the low max utilization. So this is our second challenge. Thirdly, to save the massive activation access to off-chip DRAM, we adopt activation partition and the cross-layer processing. Efficient hardware support is required for this cross-layer processing. To tackle the aforementioned three challenges, our proposed EyeCoD accelerator has the following features. First, we propose and develop a partial time multiplexing mode for workload orchestration. Based on the observation that the gaze estimation model has a lower max utilization for some of the depth-wise convolutional layers, we propose this partial time multiplexing mode and to run the ROI prediction model on the underutilized max. By using this mode, we can amortize ROI prediction workload among 50 frames, and at the same time, we can guarantee enough number of max to both of the two models to maintain a high reuse opportunity. Our proposed mode has a 2.31 times speed up and 1.6 higher energy efficiency than the time multiplexing mode and the concurrent mode. To improve the input activation reuses, we propose to use intra-channel reuse data flows. Specifically, we have column-wise intra-channel data flow and the deeper row-wise intra-channel data flow for depth-wise layers to increase the max utilization by 3 times and 2 times respectively. For the activation partition and cross-layer processing, we propose a dedicated on-chip activation memory storage layout. The right bottom figure here shows the example when storing one activation tensor. We can see that by using proper addresses, the activation partition can be easily achieved. In addition, other activation operations, including the concatenation operation, the downsampling and upsampling operations can also be supported efficiently by this on-chip activation memory storage. On top of the memory storage, we further insert a sequential write parallel read buffer between the memory and the max to provide the 2 times higher activation bandwidth for the accelerator. Okay, then Haoran will introduce the measurement results.
So next, I will introduce the evaluation setup and the results. For evaluation, we can see the IIT-NET and FBNet-C100 on OpenEDS datasets. For evaluation metric, we consider both accuracy metric and efficiency metrics, and compare the proposed ecosystem with SOTA baselines, including both the commercial devices like CPU, GPU, edge GPU, as well as the prior art eye tracking processors. So here is the platform setup in our lab to perform the benchmark with the commercial devices. And here is the setup of the EyeCoD AI accelerator, for which we tip it out in 28 nanometer technologies. And here it shows the corresponding configurations. This slide shows the overall comparison between the EyeCoD and the prior SOTA accelerators. So as we can see from this figure, as compared to the GPU platforms, EyeCoD achieved up to 40 14.8 times and 2.6 times throughput improvements over edge GPU and GPU respectively. As compared to the SOTA eye tracking accelerator, EyeCoD achieved on average 12.8 times throughput improvements and 8.1 times higher energy efficiency over the prior art eye tracking accelerator. Next, I will show the benefit breakdown of both algorithm and accelerators. So for algorithm, the eye segmentation model helps to save 16 times flops reduction over the SOTA IIT nets with a comparable accuracy of mean LOU here, which validates the effectiveness of the proposed ROI prediction. And we also evaluate the gaze estimation model. It achieves 0.04 error reductions while also reduced 78% flops compared with the award-winning model Resident 18. That validates the effectiveness of the whole algorithm pipeline. As for the EyeCoD accelerator, we here provides the performance breakdown. Overall, EyeCoD achieved 4 times speed up over the lens-based eye tracking system. To break it down, the algorithm or the predict and focus pipeline lead to about 2 times improvements, while the input, partial, and depth, which are 3 contributors in the accelerator parts, further offers 1.2, 1.3, and 1.3 improvements respectively. So to summarize, EyeCoD integrates system, algorithm, and accelerator level innovations, as we are the first FlatCam-based algorithm and accelerator code design framework for eye tracking applications. On the algorithm level, EyeCoD integrates a predict and focus pipeline to largely reduce the computational cost. And on the hardware level, EyeCoD further develop a dedicated accelerator attached to the FlatCam that can accelerate both computation and data movements. So by integrating all of these components, we can achieve the requirements we mentioned before. And FlatCam is attributed to the small form factor and improve the visual privacy. And our code design framework is attributed to the 240 FPS gains. So at last, I want to show the real demos setups here. So as shown here, this figure is the setup of the whole system, and here is the FlatCam and the chip and the demonstration to show that we can actually track the gaze directions. So that's all for our presentation. Thank you for your attention. We are open to questions.
We have time for some questions, maybe on the side. Yep, go ahead.
All right, thank you. This is Ying Jing from the University of Illinois at Urbana-Champaign. So first of all, awesome work, and finally see our work that has a tape-out chip. So my question is, you're measuring the eye tracking itself alone, but as you mentioned before in the introduction part, eye tracking can be used in AR, VR, like full video rendering. So I'm wondering if you tested, like, for example, the quality of experience for user experience, especially given the lensless camera, because, you know, if we're having a small camera, then it may not affect the user experience of looking at the display. But if you're having a lensless camera, then you're having a mask in front of the eye, and given that it's less than 2 millimeter within the eye distance. So I'm wondering if it is adding more bad effects to the user experience. And so whether it's gonna, you know, be widely used in AR, VR products or not. I don't know if you have measured that. Thank you.
Thanks, Ian, for your questions. Actually, this is a good question. I think FlatCam has good potential to be deployed in the real AR/VR devices. And as for the quality of the figure, as you mentioned, I think it needs to reconstruct the original image, right? So the quality will be less than the original image due to the loss between the encoder and decoder process. But it is still sufficient for the eye tracking applications. We can still use this to seamlessly incorporate it into the eye tracking application. As you remember, as you heard, the accuracy even gain for the gaze estimation model, we achieved 0.04 error reductions apart from the flops reduction. So that's why we adopt the lensless camera, it does not mean that we sacrifice the accuracy for the speed. We actually achieve double win. We achieve both speed up and also the quality of the images and tracking process. Yes.
Yeah, thank you. So I guess a short follow-up question is, I'm wondering if the sensor itself, by adding a mask adding a mask in front of the user eye, whether this fact is gonna affect the user experience or not.
Sorry, I think your question is that will the lensless camera influence the user experience?
Yeah, exactly.
It's not. It will provide the higher user experience. In this FlatCam camera, we can replace the lens camera of a commercial camera with the mask. So the mask is on the camera itself, and the size of the camera will be smaller. So the user experience will be better because we can have a smaller glasses without glasses like this.
Okay, awesome. Thank you.
All right, good. Let's have another question from this side of the room. Go ahead.
Hi, this is Jian Wong from UCLA. So as you mentioned, there are two phases of the algorithm, and the computing resources can be shared across these two phases of the algorithm. I want to know who's scheduling the resource allocation, and how it's determined.
Thanks for your question. So because this model is predefined, so we can schedule the resource allocation before running the model. So it's offline. And then we have on-chip controller to control chip processing. So its scheduling is offline, predefined, and we can embed it into instruction, and the controller with the instructions can run the allocation during the runtime.
So how do you switch between, different configuration of the data path?
Okay. I think your question is that how can we divide the different like MAC resources to different models?
Yeah.
This way.
Yeah.
Also, in our hardware design, we have several MAC lanes, and we can divide dynamically the MAC lanes to different models layer by layer. Yeah.
Okay.
So in the design.
Okay, we got time for one more quick question. And while we're taking that question, why don't we go ahead and get the next speaker up and switching in. So go ahead, one more quick question.
Hello, nice work. This is from University of Rochester. So I have a quick question about the lensless camera. You get a lensless camera, the image is not recognizable. The selling point is that it can preserve the privacy, right? And since you are processing everything locally, why do you have to preserve the privacy? Why can't you just directly processing the raw image instead of like you have to reconstruct the image and use the reconstruct image to process? That will introduce the overhead, right?
I think your question is that can we directly using the image, the capture image to do the following? Yes. The answer is yes, and actually the reconstructed images quality is not that high. We can even improve it. But in this design, we just simply reconstruct it and do the following models.
Yes, we can use the original image, but that will fall into the lens-based camera cases. In that way, the distance between the lens and the sensors will be slighter. So that will increase the form factor. So that is not efficient. Will not allow the eye tracking process to be attached to the sensor. So that will increase will make the VR devices more heavy, so it cannot be mounted on your head.
Great.
So that's the question.
Right.
And as for the previous question, I think you asked how we organize the workload organization. So we have the instruction set so that we can use instruction to control the operations like shuffle or the downsample, upsampling. We have instruction for it. Yeah, that's the answer.
Okay, great. We can take some more discussion offline. Let's go ahead and thank our speakers here, Haran and Yang. Let's thank them. Great. Okay, so our next speaker is Helena Caminal. She's a PhD candidate in electrical and computer engineering at Cornell University. Her research focuses on accelerating data-intensive applications using novel architectures based on associative processing. She'll be presenting her work today on using an associative processor to accelerate database analytics, and this is joint work with her collaborators at the University of Madison, Wisconsin. Helena expects to graduate at the end of the fall and is looking forward to pursuing and graduating and looking for positions in industry or in academia. All right,
Thanks,
great.
Chris. Hi, everybody. Thanks for being here. So today we're going to talk about our work on accelerating database analytics using an associative processor. This is a joint effort with my colleague Yannis, Tianshu, and our advisors Jignesh Patel and Jose Martinez. Test. Is it better? Okay, thanks. Cool. So let's start. So the value of data-driven decisions is undeniable, and as a result, data analytics are a powerful tool that require large processing of volumes of data and complex processing needs. And in fact, there are a wide variety of architectures for database acceleration, from highly efficient database accelerators to commodity processors, which trade this efficiency for generality. On top of that classification, we also find newer proposals that bring both families of architectures closer to the data. For example, some accelerators are located in the disk for very high bandwidth. And some other proposals even try to utilize the wimpy cores inside the SSD cards as well. In practice, most commercial database systems vectorize their codes to be run on Maxim units inside these CPUs. This enables a middle point between moderately increased parallelism, ease of code maintenance, and rapid adoption. And there are also some proposals that utilize GPUs for similar reasons. So in this Cambrian era of architectures, we have several options to choose from. So what is the right solution? Well, we don't claim to know what the right solution is, but we think that the direction that we should move towards is aligned with the following principles. So first, of course, being able to process large volumes of data and complex queries. But we think that we should maintain some level of generality to be able to support these rapidly evolving software, for instance, new database operators that come in. And lastly, ease of integration into existing systems, encouraging coexistence of different DSAs or different kinds of processing engines. We think that associative processors are a promising solution that aligns with these principles. They exhibit very large data level parallelism, and they support general purpose vector operations. The way that they do that is by utilizing memory devices that can search and update, which are actually operators that are found at the core of a lot of these database operations that we see. So this work is Castle, which stands on the shoulders of CAPE, which is a modern associative processor, and Hassel, which is our database processing, database management system. But first, let's dive in a little bit into what associative processing as a compute paradigm is. So traditionally, we interact with memories by indexing by address, which means we give it an address or an address and a value, and this address is read or written. Instead, associative processors or associative memories search or index by value, which means we give them a value. These values compare against all the values that are stored in this memory, and they indicate match or mismatch. So in this example, I'm showing these red flags to indicate match in these memory locations. And then the other associative primitive is update. So update will modify the same value in the locations that were matching in a previous search. So you can see that the inherent data level parallelism in this associative processing paradigm comes from these two primitives being inherently data parallel as well. And in fact, by sequencing these search and update operations, we can build more sophisticated vector operations such as vector addition and so on. So let's give a brief specific example. So imagine we want to add 1 to whatever is stored in register X6 and store the result in X5, right? So in a conventional way, we would use these half other basic blocks, and we would chain them in a way that each half other produces a sum bit and a carry bit that is propagated to the next half other. So in associative processing, we emulate the truth table of these half others, but we do that by using search and update. And we structure our data in a very specific way. So we have these A vector operand now, and each of the vector elements in this same A vector operand is stored in a different row. And then we also allocate some memory for the destination operand and some metadata. So for instance, in this operation, we would have a carry bit that we would generate and update as we go. And then we would do searches. And we would compare the key of this search across all the rows in parallel. And whenever a row matches, the tag bits for that row would be set to 1. And then subsequent operations, for instance, updates would use those tag bits to decide if that row is updated or modified. So we have a couple of optimizations. We can do more than this, but this is just an example. The first one relies on initializing the destination operand, and the second one relies on the carry bit or the metadata bit being physically located in the same memory location. So with that, we know what our microcode looks like. We look at the truth table, we have to perform 2 searches and 2 updates for each of the bits, and we emulate that for all the bits in a word. So we would start and we would search for the first useful value combination, 0, 1, in the least significant bits, A0. So note that now all the other columns not involved in this operation are masked out, indicated by this X. So it turns out that this first search doesn't match with any row. That's why none of the tag bits are set. So we could skip this update, and we go ahead and we search for the next useful entry, 1, 0, and we see that first and last rows match. So now we go ahead and update them. So now you can see we have successfully generated the least significant bit of all rows in parallel. And we would do the same for the subsequent bits. I'm not going to go over that again. But as you can see, we have generated an increment for this vector operation to all rows in parallel by performing these search update operations. And please note that this is a very small example of only 3 vector elements and 2-bit values. But in a normal system, we would have tens of thousands or more vector elements and larger bit widths potentially. So let's deep dive into our work Castle. As I said, we rely on this associative processor called CAPE, which is general purpose. It's RISC-V compatible with standard vector extensions, and it's comparable in area to one traditional superscalar out-of-order core. From the compiler's perspective or programmer's perspective, you could see this as a vector architecture of tens of thousands of vector elements. So we're not going to go into detail about each of the microarchitecture blocks here, but just know that the compute storage block, the CSV, is the main block containing all of these tens of thousands of associative arrays. And these arrays are composed of 60 push rule cells, which have a similar density to normal SRAM. So for this work, we have built the main database operators, and we have ported them into CAPE language, which would be RISC-V vector. And we have worked on several software and hardware co-design optimizations. So let me show you a highlight of our results to start with that. Our evaluation setup is based on Gem5, which we extended to model each of the blocks inside of CAPE, as well as our baseline, which is this out-of-order core with AVX512 support. And they are considered comparable in area. Our benchmark suite is the star schema benchmark, similar to TPCH. It's composed of 13 queries, which are composed of various operators. And we use a scaling factor of 1, which is about 200 times larger than CAPE's capacity. So we do model this data movement between main memory and the CAPE core, as well as for the baseline as well. So we vectorized both our CAPE codes and our baseline codes manually. So it's a highly optimized code. But for reference, the baseline code base is about 4 times faster than MongoDB. So here I'm showing the speedups of this Castle system compared with the AVX-512 core for each of these queries. And we see that on average, we were able to achieve pretty promising speedups, 10.8x, right? But actually, this was not our first results. Our first results, as you can imagine, they're never positive at the beginning. But the reason was that we focused on mapping only the database operators in isolation. So we map selection, joins, and aggregations in isolation, and we actually saw performance slowdowns when we ran these end-to-end queries. So only when we updated this database management system with new query optimization strategies, as well as enhanced this associative processor for database analytics, we were able to get to these 10.8x speedups. So let's see how we did that. So let's focus on joins for today. So a join operator tries to combine 2 tables by matching the rows based on their values. So here I'm representing both this pink and blue are matching across 2 tables. So we append the rows to generate this final table. And the way that CPUs typically perform these joins is they build a hash table for fast searching, and they search this hash table from the other table. And actually the cost of joins for CPUs is dominated by this hash table building cost. In Castle, since we have this search primitive at the core of the hardware, we just load one of the tables into CAPE, and then we search from the other table into CAPE. So actually the cost for Castle is dominated by this number of searches. So as you might already be imagining, we are swapping the probe site and the probing site in this join because of the unique features of associative processor. And of course, you can imagine that most of the time tables don't fit in CAPE. So what we do is we break these tables into chunks, and then we repeat these searches for each of the chunks. So let's see how we optimized some of the optimizations that we propose in the paper. We just have time for 2 today. The first one is the software optimization. So typically queries have more than one operator. So here I'm showing 2 joins. We're trying to combine a very large or fact table with 2-dimensional or smaller tables. And this would typically be the plan for CPU, because what is shown on the right side of a join is basically being probed by the right side. And then I'm showing here a write deep plan, which seems what I was intuitively hinting in the previous slide, which is we're trying to store the larger table or a chunk of the larger table into CAPE and then probe from the smaller table. And we see that, yes, actually, the number of searches, which is the dominating cost in Castle, is improved in the write deep plan. But actually, we can do better, right? So for the first join, we would like to probe from the dimension side, but in the second join, we would like to swap the side, right? So what we do is this zigzag plan where we swap the probe side on the fly, and we can do that by utilizing these associative processors. So the second optimization is a hardware optimization. So here I'm showing a breakdown of instructions after applying all of these software optimizations, and we see that most of the queries are actually dominated by searches. So we went ahead and we tried to optimize the cost of one single search. So for that, let me give you a little bit of context of what a search looks like on CAPE. So we bit slice our vector registers into several physical subarrays. So that means that the same bits of the same value will be distributed across different physical subarrays. So when we perform this search or vsign equal vx instruction, we have to sequentially accumulate each of these intermediate results. So we have a cost that's of the order of the number of bits. So what we propose is this contiguous mode where all bits will be contiguously stored in the same array, and we can generate the final result in very, very few cycles. But in fact, we want both modes, right? So in databases, sometimes we still need to multiply, add, and so on. And most of the time we're searching. So we care about the performance of both modes. So for that reason, we propose this adaptive layout where we are able to switch on the fly. So the compiler will insert these new instructions that will indicate a data layout switch. And we have observed that actually we don't need to transfer much information across layouts. Most of the time, the only information we need to transfer are masks. So for that reason, we have this view layout instruction that allows us to relay out a mask into a new mode. So we have worked on several other optimizations that we don't have time to talk about today. Please come talk to us if you're interested. So to recap, we have seen that we have worked on several software and hardware optimizations that allows us to achieve this 10.8x speed up. And just as a summary of my talk, I would like to say that analytics are in constant need of processing large volumes of data and complex queries. We think associative processors are promising architectures that can accelerate various types of applications, but they offer these analytic-friendly, massively parallel primitives. So who knows, maybe they could become the base for a domain-specific architecture for data processing. So Castle is a hardware and software co-design system, and we are able to achieve speedups of around 11x for with respect to an AVX512. So this is all.
All right, let's go ahead and thank Helena. We have time for questions. Maybe one question is, part of what you were exploring was software hardware co-design for databases. Do you think any of those optimizations could be backported to CAPE and be useful for general purpose computing, or are they very database specific and maybe not relevant to more general purpose computing?
So I think for the software optimizations, at the beginning, we thought they were like very database analytic focused, but actually somebody hinted at us that it could be also useful for matrix multiplication and how do you order different loops, because joins and matrix multiplication have like some similarities. In terms of the hardware optimizations, some of them I think could be used. I have some of my colleagues in my group who are telling me they could be used for genomics maybe, but we haven't looked at that yet. Yeah.
Great, we got a question on the side of the room. Go ahead.
Banyo from UCSD. So I have a question about the searching. By using the associative processing for searching, so first is the content to be searched is restricted by the table you can store. And the second question is like when you do searching, you have.
I cannot hear him very
Yeah, can you speak up a little bit?
Okay, so the first question is like, is it true that like the content, the range of the data to be searched must be some kind of smaller than your associative, like that piece of memory? And the second stuff is like, how do you comment about when you are doing search, you can have like a kind of associative like hardware to do the search and the comparison. How do you think it compares with the hash table? Because I think for hash table, you can compute the index to look up, so that you only look at one memory place.
Right.
But here you have to kind of broadcast your data to all of the memory address and do the comparison.
Right.
So kind of, I will say like in terms of memory, power efficiency, hash table you have to like activate and look up one memory address, but here you have to look up all memory address. It seems kind of more expensive. How do you comment about that?
So I think the second one was about the hash table. Like, how's it compared to hash tables?
Yes. So for the second question, so the support is built in the hardware itself. The circuits can search by themselves. You don't have to like broadcast addresses. You just broadcast keys that you compare against all of the cells. So in terms of that, that's not expensive at this scale. Probably a different memory scale, that would be a different story, like in DRAM or NAND flash or stuff like that. So yes, we see in this example in joins, right? The hash tables Building the hash table is very expensive. Once you have it, it's pretty quick. But we are able to like accelerate that by just loading the data into CAPE, and then CAPE can search on its own. We can take the first question offline if you want.
Great, good. All right, let's go ahead and thank Helena for a great talk. Okay, so the final talk of the session will be by Damla Senal-Kali. She's a staff software engineer at Bio-Nanogenomics, focusing on hardware acceleration. She received her PhD degree in computer engineering from the Safari Research Group at CMU in August 2021. She was advised by Professor Onur Mutlu and Professor Sigata. Her research interests are hardware software co-design for accelerating bioinformatic applications, genomic data analysis, and processing in memory. And today she'll be presenting her work on CGRAM, a universal genomics mapping accelerator, which is joint work with her collaborators at Carnegie Mellon, ETH Zurich, UIUC, Bill Gates University, and Intel Labs. Go ahead.
Can you hear me well? Yeah. Thank you so much for the introduction, Chris. Hi, everyone. Thank you so much for joining my talk. Today, I will be presenting our work, CGRAM. Genome sequencing, which enables us to determine the DNA sequence of an organism, plays a pivotal role in areas such as personalized medicine, outbreak tracing like COVID-19, and the understanding of evolution. So modern genome sequencing machines extract small randomized fragments of the original DNA sequence, which we call reads. And state-of-the-art sequencing machines either produce short reads or long reads. Read mapping, which is the process of mapping the reads to a reference genome, is a critical step in genome sequence analysis. And traditionally, we perform sequence-to-sequence mapping, where we map reads collected from an individual to a known linear reference genome. And this representation emphasizes genetic variations that are in the single reference genome and ignores all the other variations that could exist in the population, as you can see here. So this introduces reference bias, but as I said, this is a traditional way of performing read mapping, so it is a well-studied problem with many available tools and accelerators. So recent works replace the linear reference sequence with a graph-based representation of the reference genome, which we call as genome graphs. So with the existing of these genome graphs, we can map our reads to this graph representation of the reference genome. So this helps us to capture the genetic variations and diversity across many individuals in a population, so it results in notable quality improvements in genome sequence analysis. However, it's a more difficult computational problem with no prior hardware design. To this end, our goal is to come up with a specialized, high-performance, scalable, and also low-cost hardware algorithm co-design that alleviates bottlenecks in multiple steps of sequence-to-graph mapping. To this end, we propose CGRAM. CGRAM is the first universal algorithm hardware co-designed genomic mapping accelerator that can effectively and efficiently support both sequence-to-graph mapping and sequence-to-sequence mapping, which can be seen as a simpler variant of sequence-to-graph mapping for both short and long reads. We demonstrate that CGRAM provides significant improvements for multiple steps of the sequence-to-graph and sequence-to-sequence mapping pipelines. Let's look at genome graphs and sequence-to-graph mapping in detail. As we said, genome graphs are better suited for expressing the genomic regions that have variations than a linear reference sequence, since genome graphs combine the linear reference genome with the known genetic variations in the entire population as a graph-based data structure. Genome graphs enable us to remove the reference bias that using a single reference genome introduces, and therefore there's a growing trend towards using genome graphs to more accurately express the genetic diversity in a population. Let's look at an example. Let's say this is our starting linear sequence. So we can start with a single node, but let's assume in the population, we have also this alternative sequence where on the fourth position, we observe a G instead of a T. So there's a substitution. What we can do, we can divide this node into two nodes for representing the common subsequences, have one path to representing the first sequence, and have another path for the second sequence. And let's say we have a third one. In this scenario, we have an insertion on the fifth position with a T. So we can have an additional node in our graph to represent this third sequence. And let's say we have a fourth one where that on the fourth position, the T doesn't exist at all, so there's a deletion. So we can have a direct path from the first node to the last node. So with increasing importance and usage of genome graphs, having accurate and efficient tools for mapping genomic sequences, the reads, to these genome graphs has become crucial. Which brings us to sequence-to-graph mapping pipeline. So this pipeline has two pre-processing and three main steps. And the first pre-processing step constructs a genome graph using a linear reference genome and the associated variations for that genome. And in the second pre-processing step, we index the nodes of the graph, and the resulting index is used in the first main step of the pipeline, which is seeding, which aims to find the seed matches between the query read and a region of the graph. After optionally filtering, clustering, or chaining these matches, alignment is performed between all of the non-filtered seed locations within the graph and the query read to find the optimal alignment. So alignment is the most expensive step of this pipeline, so let's look at it in detail. Traditional sequence-to-sequence alignment typically employs a dynamic programming-based algorithms with quadratic time and space complexity. A DP-based algorithm operates on a table, as you can see here, where each column of the table corresponds to a reference character and each row of the table corresponds to a query read character. And in sequence-to-sequence alignment, a new cell, which you can see here, the dark blue one, the table is determined with simple rules from three of its neighbor cells. Whereas in contrast to sequence-to-sequence alignment, when we look at sequence-to-graph alignment, we have to incorporate non-neighboring characters, which are the hops actually, so which can be coming from non-neighboring cells. For example, here for the green shaded cell, we have to incorporate the three neighboring cells, but also two other non-neighboring cells as well. In order to further understand the performance bottlenecks of the state-of-the-art sequence-to-graph mapping tools, we rigorously analyze two such tools, Graph Aligner and VG, and we make four key observations. First, among the three online steps of the read mapping pipeline, alignment constitutes majority of the end-to-end execution, plus it is even more expensive than its counterpart in the sequence-to-sequence mapping pipeline. Second, this alignment step suffers from high cache miss rates because we are generating and reusing a lot of internal data. And third, seeding step suffers from the DRAM latency bottleneck because we are doing a lot of irregular memory accesses to the main memory. And fourth, both of the tools scale sublinearly. So because these problems exist, we also look at hardware accelerators, but as I said, there's no hardware accelerators specialized for sequence-to-graph mapping. So we looked at existing sequence-to-sequence mapping accelerators, but they are unsuitable for the sequence-to-graph mapping problem because they cannot handle the graph-based inputs, the reference genome. So we looked at existing graph accelerators because we have many of them, but they are promising for solving the seeding problem when querying the main memory, but they are unable to handle the actual bottleneck problem, which is alignment, because alignment is not a graph traversal workload. So we need to have a specialized, balanced, and scalable design for compute units, on-chip memory, and also main memory accesses for both the seeding and alignment steps of sequence-to-graph mapping. To this end, we propose SIGGRAM. SIGGRAM is the first universal genomic mapping accelerator that can support both sequence-to-graph mapping and sequence-to-sequence mapping for both short and long reads. And to our knowledge, SIGGRAM is the first algorithm hardware co-design for accelerating sequence-to-graph mapping. And we base SIGGRAM upon a minimizer-based seeding algorithm, and we propose a novel bit vector-based sequence-to-graph alignment algorithm. So these are our algorithmic contributions. We co-designed both algorithms with high performance, scalable, and efficient hardware accelerators, and this covers the hardware level contribution of SIGGRAM. So when we look at the SIGGRAM hardware design, it consists of two main components. First, MinSeed, which is responsible for the seeding step, and it is the first hardware accelerator for minimizer-based seeding. And second component, BitAlign, is responsible for the alignment step, and it is the first hardware accelerator for sequence-to-graph alignment. Let's look at the high-level overview of SIGGRAM. So before SIGGRAM execution starts, as pre-processing steps, we generate each chromosome's graph structure, index each graph's nodes, and then preload both the resulting graph and the hash table-based index into the main memory. So both of these data structures are static, so we can generate them only once and reuse for multiple mapping executions. So let's look at the overflow. So SIGGRAM execution starts when the query read is streamed from the host and MinSeed writes it to its scratchpad. And using all of the K-length subsequences, which are called K-mers of the query read, MinSeed finds the minimum representative set of these K-mers, which are called minimizers, according to a scoring mechanism, and writes them to the minimizer scratchpad. And for each minimizer, MinSeed fetches its occurrence frequency from the hash table sitting in the main memory and filters out each minimizer whose frequency is above a user-defined threshold. And here we aim to select the least frequent minimizer so that we can decrease the burden on the alignment step. Next, MinSeed fetches the seed locations of the remaining minimizers from the main memory and writes them to the seed scratchpad. And finally, MinSeed calculates the candidate reference region, which is the subgraph surrounding the seed. For each seed, fetches the graph nodes from the main memory and writes the nodes to the input scratchpad of BitAlign. And then BitAlign starts by reading the subgraph and the query read from the input scratchpad and generates the bit vectors required for the alignment operation. So while generating these bit vectors, BitAlign writes them to the hop queues in order to handle the hops required for graph-based alignment, and also to the bit vector scratchpad to be later used as part of the traceback operation. And once BitAlign finishes generating and writing all these bit vectors, it starts reading them back from the bit vector scratchpad, performs a traceback operation, finds the optimal alignment between the subgraph and the query read, and streams the optimal alignment information back to the host. When we look at the hardware design of MinSeed, it consists of 3 computation modules, 3 scratchpads, and the memory interface. So the computation modules are implemented with simple logic since we require only basic operations like comparisons, simple arithmetic operations. And for all the 3 scratchpads, we employ a double buffering technique to hide the latency of the MinSeed accelerator. And we also couple MinSeed with high bandwidth memory to enable low latency and highly parallel memory access. When we look at the hardware design of BitAlign, we implement it as a linear cyclic systolic array-based accelerator. So while this design is based on the GNASM hardware, where bit vectors are written to bit vector scratchpads during bit vector generation step for later use in traceback, our new design incorporates hop queue registers in order to feed the bit vectors of non-neighboring characters or nodes, so the hops. And when we look at the overall system design of SIGGRAM, it is connected to a host system that's responsible for the pre-processing steps and for transferring the query read to the accelerator. And next to each HBM channel, we place one SIGGRAM accelerator such that it will have exclusive access without any interference from other SIGGRAM accelerators. And each SIGGRAM accelerator is a combination of one MinSeed accelerator and one BitAlign accelerator. So each HBM stack has 8 memory channels, so connected to 8 SIGGRAM accelerators, which define one SIGGRAM module. And our hardware platform includes 4 off-chip HBM stacks. So we have 4 SIGGRAM modules in total, so 32 SIGGRAM accelerators in total. As a result of the flexibility and modularity of the SIGGRAM framework, we can run each accelerator together or separately. So we describe 4 use cases of SIGGRAM. And the first one is end-to-end mapping with SIGGRAM, where we need to run MinSeed and BitAlign together. Second, we can have a sequence to graph alignment as our use case where bit align will be standalone, but it can be coupled with any seeding alignment, seeding tool or accelerator. Similarly, we can use it for sequence to sequence alignment. And our fourth cases, use case is seeding for both linear or graph-based mapping, where we will be running standalone min seed, but it can be coupled with any alignment tool or accelerator. Let's look at our evaluation of the SIGGRAPH design. So I won't be able to go into details of our methodology, but you can refer to our paper or we can talk offline. But based on our synthesis of the min seed and bit align accelerator data paths, total area overhead of SIGGRAPH attached to all 32 channels is around 28 millimeters square, and the total power consumption is around 28 watts, including the HBM power. And we find that main contributors for the area overhead and power consumption are hop queue registers, since they constitute more than 60% of the area and power of bit align logic, and also the bit vector scratch pads. Let's look at our long read analysis for sequence to graph mapping with SIGGRAPH. Here we only show our throughput numbers in the plot, not the power numbers. So we compare SIGGRAPH with two state-of-the-art sequence to graph mapping software tools, Graph Aligner and VG. And we find that SIGGRAPH provides around 6 times and 4 times throughput improvement over these baselines, while reducing the power consumption by more than 4 times for both. And with the exact same baselines, but this time with short reads, we find that SIGGRAPH provides even higher amount of throughput improvement over both of these baselines, while reducing the power consumption by, again, more than 3 times for both. And let's look at our key results for the sequence to graph alignment use case, where we are running bit aligns as a standalone, and we compare it with software-based tool Pascal. And we find that depending on various data sets, as you can see here, bit align provides between 4 times to more than 500 times speed up over Pascal. And as we said, bit align can also be used for sequence to sequence alignment, but the cost of more functionality is extra hop queue registers in order to support sequence to graph alignment as well. But we don't sacrifice any performance for either use cases. So compared to state-of-the-art hardware accelerators, but this time specifically designed for sequence to sequence alignment, we find that bit align increases throughput for over all 3 baselines, but with the extra cost of power consumption and area overhead. So before I conclude, here's a list of additional details that you can find in our paper. For example, sources of improvements in SIGGRAPH. So to conclude, in this work, we propose SIGGRAPH, the first universal algorithm hardware co-designed genomic mapping accelerator that supports both sequence to graph mapping and sequence to sequence mapping for both short and long reads. SIGGRAPH consists of 2 components, min seed and bit align, and it supports multiple steps of sequence to graph and sequence to sequence mapping pipelines. And based on our extensive analysis, we show that SIGGRAPH outperforms state-of-the-art software and hardware solutions. So our paper is available online, and we will be releasing our software implementations and the data sets we use in our GitHub page soon. Thank you so much.
We got time for a question or two. Maybe one question about the hop queue. So it seems like one of the key differences between sequence to sequence and sequence to graph is these additional edges. And I think those are tracked by the hop queues. It seems like the hop queues would have to be quite large to capture very long hops. So how do you navigate that trade-off?
That's a really good question. So there is a trade-off there. We cannot, of course, the graph can be huge, even though we are generating them per chromosome. But in SIGGRAPH design, we limit our hop queue register size as 12 based on our empirical analysis, because when we do that, we found that we cover more than 99% of all the hops exist in the generated graphs. So we lose some hops with this design choice, but we save significant amount of area and also power as well.
Okay, go ahead. Yep.
Yeah, thank you for this talk. Just a quick question.
Don't forget to introduce yourself.
So is there a specific reason why you choose to use HBM? And the second part is if you want to use this approach, which let's say standard DRAM, how will you do?
So could you please
I think
repeat?
he's asking
the-
about HBM.
Yeah.
Yeah,
Specific
Yeah.
reason to choose to use HBM or, and then the next part of the question is if we want to use standard DRAM, how?
Right. That's a really good question too. So the reason why we pick HBM is just to have exclusive access for a portion of the memory. So they won't be interfered, the multiple accelerators won't be interference with each other. But the high band, like bandwidth, memory bandwidth requirement is not that high. So we are not exploiting that. So which kind of answers your second question. We can definitely attach a typical DDR kind of memory to SIGRAM. The only thing we have to add on top of is the memory access management. That's it. Yeah. Thank
We
you.
got time for one more question.
Hi, great paper. Just wondering, what were the read sizes like for long reads that you were looking at, like N50 or something?
Yeah, 10,000 we
Okay.
picked.
Okay.
They are simulated reads.
Okay. How much would you like? How would you think the performance is going to change? Like, is there like some sort of a read size limit that would affect the performance?
Yeah, so that's a good one too. So we are following a divide and conquer approach where we are dividing our inputs into chunks so that they won't be dependent on our mechanism won't be dependent on the inputs. So it will scale linearly because just the number of windows will increase in that scenario.
Right. And for the read errors, what's the percentage at which you feel like that the performance is like not good?
So we picked 5% because the technologies are around
Right.
that bar these days. So when we look at different error profiles, again, it is just a constant with our this approach in our underlying algorithm and also the mapped accelerator as well. So
Thank you.
Thank you.
All right, great. So let's go ahead and thank Damla. And this does conclude this session. So I think now we have a break.